Hi friends, today we'll see what are the basic solar things of the solar energy if you want to produce the solar energy. So see, we need to know some things. Without the knowledge, we cannot directly design the photovoltaic cells. We cannot directly tap the energy, solar energy. So in our previous session, we have discussed about what are the things which is present in the sun. So the star of our solar system, that is the sun. So what's happening is that the nuclear fission is the cause for that energy in the core. The nuclear fission in the core is the cause for that, and so it consists of so many layers and electromagnetic belt. So it consists of corona. So finally, we have concluded that the enormous of light and heat, enormous amount of light and heat will be released in this process from the sun. So after that, after what is happening to this energy, so this energy is traveled to this energy and light is traveled to the universe. It will not stay there. It will move. And of course, after the energy is going to dissipate or disperse. So this energy is reaching to if you take the solar system, this energy is reaching to all our planets, 9 planets, and they are receiving. And based on their inclination, their revolution and rotations, and the day and night are extremely different. So we cannot. So we are calculating the time based on the sun. So why the time is existing? So this is if you think seriously, why the time is existing. So it is due to the revolution and rotation. So this revolution and rotation varies for different planets in our solar system. So for us, it is 365 days and 24 hours a day. And here is the 365 days. But it will vary for the Mars. It will vary for the Mercury. It will vary for the Venus. For example, if you observe the Venus in our planet, so the day is more than the year there. The day is more than the year there. So that is a extremely different. So time is varying based on our Earth's, based on the planet's revolution and rotation. So here, okay, this energy is reaching all the planets, and they are having different atmospheres. Of course, they are not having the life there. Only the planet is the Earth. So that's why for the life on the Earth is directly and indirectly, Sun is the foundation. Sun is the basic source of energy. And what are all the power engineering? We are power production engineering. We are talking. They are directly, so sun energy, photon energy is directly converted into electrical energy, wind energy. So that is indirectly due to the heat of the sun, and whatever the hydro, water. So they are directly or indirectly related to the sun. So that's why it is very important. So after that, so it is reaching to the Earth. So before reaching to the Earth land, so it has to come across the massive environment around this Earth. So there are so many layers: troposphere, ionosphere, stratosphere, which are different, which are unique by themselves. So it has to pass there. So if you observe the light of the sun, it is a spectrum. We can say 7 colors. So why we are getting 7 colors? So we will get 7 colors based on the wavelengths. Of course, its velocity is 3 into 10 power 8 meters per second, and the time taken is 8 minutes and 20 seconds. And if you observe the gamma rays, approximate wavelength in meters, 10 power minus 14, X-rays 10 power minus 12 to 10 power minus 10, ultraviolet rays 10 power minus 8, and if you observe infrared rays 10 power minus 6 to 10 power minus 4, and microwaves 10 power minus 2, and radio waves 10 power 2, 10 to 10 power 2. So that is the, based on this wavelengths, we have categorized different rays. So if you are watching a blue color, it's blue because it's a high energy photon. So if the light is blue light, so there the photon is high energy photon. It's a high energy photon. If you are observing a red color, it is a low energy photon. And it is infrared light, so you cannot see. So it is low energy photon again there. So if you go to the radiation of the sun, so what is the visible light? So more than some wavelength we cannot see, and less than some wavelength we cannot see. So that is between 0.4 to 0.71 micrometers. And sun emits only a portion, 44% of its radiation in this range. So out of the energy which is emitted by sun, so which is in the visible spectrum comes under only 40%. Remaining it is not coming under the visible spectrum. So that is about the sun's radiation. And the energy, the sun rays, which is coming to the earth. So before coming, it has to face the earth's atmosphere. So it is, we are calling it as the true radiation. It is coming reaching the earth. So before coming to the earth, so much amount of energy is diffused or altered. So it is not coming as it is to the earth. So before it is coming, it is facing the earth's atmosphere. So it is losing some of its energy there. So some rays, yes, they will come with full energy, some with moderate energies. So they will differ. And so not all the rays are direct rays. So majority are almost 50% are diffused rays which are reaching to the earth. If you observe there, in this PPT you can observe. So nearly 49% is not reaching to the earth, the sun. So only 51% is reaching to the earth. So again in this 49%, 4% is reflected back to the earth, back to the earth's surface, and 26% is scattered or reflected to the space by the clouds and atmospheric particles, and 19% is absorbed by the atmospheric gases, particles and clouds. So we have discussed 51% is reaching the earth directly. So 41% is tapped by the atmosphere of the earth. Tapped by the atmosphere of the earth. So again in this 49%, 4% is again reflected back to the earth's surface, and 26% is scattered, and 19% is absorbed by the atmospheric gases. So you can if you observe what is the energy reflected back. So at the equator, so almost only at the poles, majority of the energy is reflected back, again in this 4%. So that is not useful thing anyway. That 4% is very less, and again it's concentrated only on the poles. So if you observe here, so this is 100% is coming there. So you can conclude from this. Okay. So here 100% is coming, 50% is absorbed at surface. So 51% is reaching to the Earth, and 19% is absorbed by the atmosphere, and 4% is reflected back, and 20% is by the clouds, and 6% reflected by the atmosphere. So that means only half of the energy is reaching to the Earth. So we can use only this half of energy of the total energy of the sun, which is reaching to the sun, which is reaching to the Earth before it is touching the soil. Again, 50% is lost due to the Earth's atmosphere. So here also you can see, you can observe here. So in that 51%, this is a direct beam. So which is not diffused. This is sky, and this is the direct beam, and this is isotropic diffuse, and this is circumsolar diffuse, and diffuse from the horizon, and this is the reflected from the ground back. So this is a solar panel. So this is directly, this has come directly, and this is not direct, it's somewhat diffuse, isotropic diffuse, and this is circumsolar diffuse, and diffuse from the horizon. So the sun is there, it's coming like this. It's not perpendicular, it's not coming perpendicular, it is coming parallelly to that surface, and this is the reflected back to the from the ground to the panel. So these many different types of rays. We will think that generally what we will think that we'll think is that sun energy is coming and falling on the PV cell, and it is making. So we don't know. So almost 50% is already lost in the atmosphere, and in that 51% also, even that 50% is not direct. Direct energy is very, very less. So remaining is diffused and reflected from the back from the ground. And other problem is that shading effect. So if you have to arrange, so one array, in that back you will be having another array. So at one point, because the sun is moving, so the shadow of the earlier front array will fall automatically on the back array. So this is also one of the typical disadvantage. So if you observe the mean daily solar radiation, so what is the radiation in the Northern Europe, Southern Europe, and Southeast Europe and Sahara Desert, Southeast Asia and Sahara Desert, you can observe. So how much direct ray energy, direct rays you are getting, and how much diffused rays you are getting. So you can observe here. So if you observe the Northern Europe, so Northern Europe, Sweden, Norway, England, almost Denmark, Iceland, France. So all this come under Northern Europe. And if you observe there in January, so it's getting almost diffused. It is almost getting the diffused rays. And February somewhat, but total in January it is getting totally diffused rays. In February almost diffuse only a little bit. On Mars, slowly it is increasing its. So they will get very good direct energy without diffusion. That is from the May to August. Actually, we are also getting good from. We will get from March. We'll get from March to June actually. So because of that positions, that is different, and it has slowly increased, and again it will slowly decrease when it's coming to the December. Again, totally only diffused energy they are getting. So the diffused energy means it is decreasing the efficiency. If you come to the southern Europe, because somewhat near to the equator, the picture is very much better when you compare to the northern Europe and southern Europe. So almost from the starting, the direct rays is dominating. Similarly, if you go to the desert, very good direct energy it is getting in the Sahara Desert, which is very economical. Southeast Asia, it is varying. So January, March, similar to us, March, it is more. Again, May, it is more. June, July, June again, it has decreased. So our climate is a very different climate. And solar radiation. All substances actually, they will release the energy in the form of electromagnetic waves. That's why which is called as the radiation. A perfect black body emits energy from its surface at a rate q. So q is equal to sigma a to the power 4, and sigma is Stefan Boltzmann constant, that is 5.67 10 power minus 8 W per meter square, K4, and A is the heat transfer, A is the normally area, it is in meter square, and T is the absolute temperature. So epsilon is the radiation emission of a real body by radiation emission of a black body. So epsilon is the MCT of the surface. So finally, the surface is the which is the thing which is going to emit. So what happens actually if it is reaching, the rays are reaching some body. So this is the direct ray actually. Some amount is reflected back and some amount is absorbed by that material and some amount will transmit. So it will go through it and come out of that. So that's actually going to happen. So the solar constant is the energy received from the sun per unit time on a surface of unit area kept perpendicular, not parallel, exactly perpendicular to the radiation in the space just outside the Earth's atmosphere when the Earth is at its mean distance from the sun. So when Earth is at shortest distance from the sun, if you put the that area above the atmosphere, the perpendicular. So perpendicular, the sun rays is perpendicular. So what is the energy it is received per unit area in unit time? So that is so its standard value is 1353 watts per meter square, and it is given by 1s is equal to 1 point. So n is the number of days. Okay, 360 by 365 day of the year. Okay. So this is the calculation which is actually. So again here that's why we are calling it as. So what is the energy which is able to reach? Okay, even the diffused energy, including with the direct energy and diffused energy. The energy which is able to reach the Earth, we are calling it as terrestrial energy. Terrestrial. And terrestrial radiation, and which is unable to reach the Earth, which has stopped in the atmosphere. We are calling it as extraterrestrial radiation or energy. Okay. So here also you can observe. So based on the different data, yes, we can observe here in different analysis. So 100% is coming from the actually coming to the surface, Earth's atmosphere. So in that ozone will be from 20 to 40 kilometers. So it is 2%. So we had told that in our previous slides, 19% is totally absorbed by the in that 2% by the ozone, and 1% upper dust layer. So there will be upper dust layer on the atmosphere. So it will be 15 to 25 kilometers. So it absorbs to 1%. And air molecules will be from 0 to 30 kilometers. And they will be absorbing 8% of the energy. And water vapor will be from 0 to 3 kilometers, and it will absorb 6%. So upper dust layer, first actually ozone, next upper dust layer, next air molecules, next water vapor, next lower dust layer again. So it will be from 0 to 3 kilometers, and it will absorb 1%. And they are telling it is going to give 70%. No, it's including the other which is not absorbed by the layer, but it is scattered actually. So again, in this 3% is back from the air molecule, 1%, and 0.5% from the water vapor, and 1% of lower dust. It will go back to space. 3% is reflected back to space. So this is actually happening. And the next thing is that air mass. So it is the shortest path the sun ray will take to reach the Earth. Okay, the air mass is the path length, which takes through the atmosphere normalized to the shortest possible path. So it is 1 by cos theta, where theta is the angle from the vertical zenith. Vertical. So this is suppose Earth is flat. So angle from the vertical zenith. So if it is sliding, angle vary. Actually, it should be exactly perpendicular. So that is called the air mass. So it is the shortest possible path the sun ray will take to reach the Earth. Here you can observe. So this theta is the angle. So if it is at the midday, it's J, but it's not. So again, it has varied to 45 degrees. It's exactly perpendicular. Now it's not perpendicular. So at this stage, you will get good energy. Here, you will not get quality of energy. Motion of the sun. So the motion of the sun, everybody is aware of this. So we have discussed how much energy is lost in the Earth's atmosphere, but after it has escaped from the Earth's atmosphere, again there are so many constraints, because sun will be moving, because the Earth is having different geographical structures. So in that one point, the sun will be moving. It will be constantly moving from east to west. You can observe here. So it is moving. So this is north, this is south, west and east. So he is moving. So based on that angle, you will be getting shadow. The energy is going to vary. And the declination angle. Okay. So it is denoted by the theta, very seasonally. So normally, because of Earth is not exactly, it will not be, it is inclined. It rotates in a inclination. That's why you will get 6 months sun at the North Pole and 6 months sun at the South Pole. So the declination angle is denoted by a del and varies seasonally due to the tilt of the Earth on its axis and rotation of the Earth around the Sun. If the Earth were not tilted on its axis of rotation, the declination would be 0. So if it is like this plus 23.45 plus, so that is where the North Pole is going to get the light, and 23.45 minus, that is where the South Pole is going to get the light. So it will be moving. So only at the equinox, so it will happen only 2 times in a year. So only at that time the angle will be exactly 0. So that we have to keep in mind. So here, so where the equinox happen in the September 23rd and March 22nd. Okay, March 22nd and September 23rd. So there is no declination of the Earth. So it will be exactly 0. Okay. So remaining time it will be exactly at June 21. So the declination is 23.45. And December 22nd, declination is minus 23.45. That we have to keep in mind. So here, so actually, if the angle is 0, the rays will fall exactly perpendicular to the surface of the Earth. It will reach exactly perpendicular because it is inclined. They are falling at some angle. You can observe here. So this is actual sun. This is because of the inclination of the Earth. So this is the angle of declination. So this is the angle of declination when it is 23.45 angle. So which is happening in the June 21. So here we will get the north. So full light at the North Pole. And similarly, equinox. It is equinox at March 22nd. And again equinox at 23rd, September 23rd. And again declination minus 23.45. So like that it is going to happen. So next thing is the elevation angle. So good. It's good. The sun is moving. So at the sunrise, it will be 0. The elevation angle. At the sunset, it will be 90. So if you with this diagram, so sun is moving east to west. You can observe. So it is the elevation angle is the angular height of the sun in the sky measured from the horizontal. So here you can observe. So this is horizontal line. This horizontal line. So this is the angle between this North Pole and South and this sunlight. So this is the elevation angle. Both altitudes and elevation are also used to describe the height in the meters above sea level. The elevation is 0 at sunrise and 90 at the sunset. Uh, uh, at sunrise and 90 when the sun is directly overhead. So, okay. And it is overhead, it is exactly 90. If it is 90 means you are getting very good. And 180, again it is equal to 0. So the elevation angle varies throughout the way. So from 0 to slowly it will go to 10 degrees, 20 degrees, 25 degrees, 30 degrees, 45 degrees, slowly, and 90 degrees at the mid of the day. And slowly it will 100 like that. So slowly it will move to 180. So it is totally varying. So azimuth angle. This is a different thing. So azimuth angle is a different thing, different way of observing the sun. So we will take the north and south pole as a reference here. So the angle of the north and south pole to the rays of the sun, to the sun rays. So that is the azimuth angle. So the azimuth angle is the compass direction from which the sunlight is coming. At solar noon, the sun is always directly south in the northern hemisphere and directly north in the southern hemisphere. So exactly at mid of the day, it will be directly south at the northern hemisphere and at the north at the southern hemisphere. So this is also moving. So there with the horizontal line, here with the vertical line, we have to say. So there with the horizontal line, here with the vertical line. So that is the north and south pole reference line. So at the equinox, the sun rises directly east and sets directly west, regardless of the latitude. So only at the equinox we will be having this type of thing directly without varying the latitude. No need for thinking about the latitude. Thus making the azimuth angle 90% at the sunrise and 270% at sunset. So that is exactly, that is perpendicular at sunrise and sunsets. So you can observe here. So 90. So what is sun rays at the exact at the sun rising time? If you observe with the north pole, it is exactly making 90 degrees, and sunset it will be 270 degrees. So the angle between. So we will take north pole as the 0. Okay. So from 0 to 90 degrees at the sunrise and 270 at the sunset. So that is the azimuth angle actually. So this here also you can see the sun rays. So this is the azimuth angle. So it is approximately 45 degrees. So from here, exactly from the north line, north and south line to the sun rays falling here. So if you draw a line like this, and this line will give the azimuth angle. This line will give the azimuth angle. So this is about different. And what are the different things by the atmosphere? Is that atmosphere is capable of absorbing almost 50%, and remaining 50% also it is capable of releasing it, majority of releasing after diffusion. So only direct radiation So there is some amount of energy. So that we'll be calling it as the direct radiation. We'll be calling it as the direct radiation and diffuse radiation. So after it has loosed some of the, if it has been affected by the atmosphere, and after then also it is able to reach. So you can observe in this picture. So this is the sun. So this is the atmosphere, and here this is absorbed, and this is directly. This is the direct sun rays, and from the atmosphere it has diffused. Actually, it has to pass like this. Directly, it has to reach the surface. It has to reach the ground. Actually, here you can observe. So this has to reach the ground. What happened there? It has diffused in this direction. It has changed its direction because of the atmosphere. Okay, so that's what. Actually, that is the problem. Okay, so that's why we can say that there is so much of energy lost there. And again, you see this. This is what happening. The cloud is in between. It has reflected it back to the atmosphere. So these many different things are happening for the sun energy before it is reaching to the Earth's surface. After reaching to the Earth's surface, again some of energy is reflected back from the ground. It is reflected by the ground. That's simple explanation we can give with this diagram. And also the thing is that the pollution also plays a key role in this energy loss, along with this atmosphere, water vapor, clouds, upper dust layer, lower dust layer, okay, water molecules layer, ozone, all these things. Along with that, the pollution is also playing some significant role in this. So that means it is also giving some loss to the direct radiation, some loss for the direct radiation. And so this is actually, and along with these things, it is differing, the terrestrial radiation. So if the direct radiation is also falling on the rocky, on the hill, on the rocks, on the desert, on the tree, on the sea. So this also plays a difference. This also makes a difference. So if you go to the area where it is rocky, if you go to the area which is of desert, it's different soils. So based on this also show their impact on the production of the electrical power. Along with the seasons, so we have discussed about the azimuth angle, okay, azimuth angle, elevation angle, all these things, but declination angle, motion of the sun, air mass, all these things we have discussed. But and also the seasons play a very significant, very dominating effect. So in the summer, okay, the angles will be same, the azimuth angle is same for as the remaining days, but it is summer, it will vary for the energy tapping capacity varies from summer and winter and for rainy seasons because of the water vapor in the atmosphere and because of the clouds. So this also plays a vital role in making our electrical energy from the sunlight. Thank you. Thank you very much. Thank you for listening.
Like, share and subscribe. Hit the bell icon for more updates.